September 14th, 1815, Hampshire. Dawn breaks cold over the river Test, and inside a Georgian silk mill, 20 wooden looms shake the floor with their rhythm. They've been running since midnight. The weavers work by candlelight, their hands moving through motions learned in childhood, fingers threading silk that arrived from China 6 months ago. The looms themselves are older than anyone in the room. They were built in 1790. The water wheel outside turns at 8 revolutions per minute. Steady, predictable, the same speed it turned yesterday, the same speed it will turn tomorrow. What no one knows yet is that these looms will outlive the water wheel. They'll outlive the steam engine that replaces it. They'll outlive the electric motors that come after that. They'll outlive the weavers, their children, their grandchildren. They'll outlive the British Empire itself. Because at Whitchurch Silk Mill, the machines were never designed to be replaced. They were designed to run forever. This is the story of engineering that refused to die. The mill sits on the Test, one of England's clearest chalk streams. The location wasn't chosen for beauty. It was chosen for power. Water flows here at a consistent rate year-round, unlike most English rivers that flood in winter and dry in summer. The Test delivers energy with the reliability of a metronome. The original mill owner, a man named Henry Portal, understood something fundamental. Silk production requires precision. The threads are finer than human hair. Tension must remain constant. Speed must never vary. One fluctuation ruins an entire bolt of fabric worth more than a weaver's yearly wage. So Portal built looms from oak and brass. No shortcuts, no compromises. The frames were mortise and tenon joints, same construction as cathedral roofs. The gearing was cut by hand, each tooth filed to exact specifications. The shuttle mechanisms were bronze, not iron. That's because bronze doesn't corrode in Hampshire's damp air. The water wheel was 30 feet in diameter, cast iron rim, wooden buckets. It turned a main shaft running the length of the building, a single piece of greenheart timber from South America, chosen because it's harder than English oak and doesn't warp. Every loom connected to that shaft through leather belts. The system was simple, elegant, and it worked for 73 years. Then in 1888, the river betrayed them. Not through flood or drought, through arithmetic. The mill had expanded, more looms, more production. The Test still delivered the same 8 revolutions per minute it had always delivered, but now that wasn't enough. They needed more power than water could provide. The owners faced a choice that terrified them. They could abandon the mill, relocate to industrial Manchester, where steam power was abundant. They could reduce production, accept smaller profits. Or they could do something no silk mill in Britain had successfully attempted. They could keep the same looms and change the world around them. They chose the third option. A steam engine arrived from Bolton in November 1888. 40 horsepower. It was installed in a new brick building beside the original mill, connected by a drive shaft through the wall. The engineers faced an immediate problem. Steam engines run at variable speeds. They respond to throttle pressure, to coal quality, to boiler temperature. The silk looms required the same steady rhythm they'd known for 73 years. The solution was a governor system, a spinning assembly of brass weights and springs that regulated engine speed through centrifugal force. When the engine ran too fast, the weights flew outward, closing the steam valve. When it slowed, they dropped, opening the valve. Self-correcting, mechanical intelligence built from metal and physics. They started the engine on December 3rd, 1888. The looms shuddered, the weavers held their breath. Then the rhythm stabilized, the same 8 beats per minute they'd known their entire lives. The looms didn't know they were being powered by steam instead of water. Why would they? Their world consisted of belt tension and thread tension. The source of rotation was irrelevant. They wove silk for another 38 years under steam power. But 1926 brought another change, this time driven by economics rather than capacity. Coal was expensive. Labor to feed boilers was expensive. Maintenance was expensive. Meanwhile, electricity had arrived in rural Hampshire. The new technology promised constant power at predictable cost, delivered through copper wires instead of coal wagons. The owners made another decision: keep the looms, change the power. An electric motor was installed in 1926. 25 horsepower, manufactured in Manchester. It connected to the same main shaft that had received power from the water wheel in 1815 and the steam engine in 1888. The engineers faced a different challenge this time. Electric motors run at 3,000 revolutions per minute. The looms needed 8. The solution was a reduction gear system. Multiple stages of gearing that transformed violent electric rotation into the gentle, steady rhythm the silk required. The first gear reduced the speed by a factor of 10. The second by another factor of 30. By the time rotational energy reached the main shaft, it moved at exactly the speed it had moved for 111 years. They threw the switch in March 1926. The motor hummed. The looms shook. Then they settled into their rhythm, the same rhythm, always the same rhythm. The weavers returned to their work. Different grandchildren now, 3rd and 4th generation, but the hand motions were identical to those their ancestors had learned in 1815. What makes this story remarkable isn't that the mill changed power sources 3 times. Industrial buildings do that. It's that the same looms, the actual physical machines, operated continuously through all 3 transitions. No replacements, no upgrades, the same oak frames, the same brass gears, the same bronze shuttles that Portal's craftsmen had built in 1790. Compare this to modern manufacturing. A smartphone factory replaces its production line every 2 years. A textile mill in Bangladesh operates looms designed to last 5 years before planned replacement. We build for obsolescence because replacement generates profit. But Whitchurch Silk Mill was built during an era when replacement wasn't an option. You couldn't order new looms from a catalog. If your equipment failed, you were finished, so you built equipment that couldn't fail. The looms at Whitchurch represent a philosophy we've lost, as they were designed with the assumption that maintenance would always be cheaper than replacement. Every bearing could be reground, every shaft could be relathed, every broken part could be fabricated by a competent machinist with basic tools. There were no proprietary components, no sealed assemblies, no planned obsolescence, just honest engineering built from materials that improve with age. The mill operated under electric power until 1990, when international silk competition finally made British production uneconomical, not because the looms failed, They never failed. But because you can't compete with Chinese labor costs when your equipment is 200 years old and designed for quality over speed, the mill closed. The looms stopped. For the first time in 175 years, silence. But this isn't a story about defeat. It's a story about what's possible when you build without compromise. In 1994, the mill reopened as a working museum. The same looms that wove silk for Wellington's army now weave silk for tourists and specialty orders. They're powered by electricity, same as they were in 1990, but the system works exactly as it did in 1815. Because good engineering doesn't care about decades. It doesn't care about technological revolutions. It just works. Walk through Whitchurch Silk Mill today. Stand beside those oak-framed looms. Watch the shuttles fly back and forth, all brass fittings gleaming from 2 centuries of friction polish. Listen to the rhythm, 8 beats per minute, same as always. Then ask yourself, what have we built in the last 50 years that will still be running in 2020? The answer is uncomfortable. We've built planned obsolescence. We've built software updates that brick hardware. We've built sealed components and proprietary parts and devices designed to fail precisely when the warranty expires. Whitchurch Silk Mill stands as an accusation. It proves we once knew how to build things that lasted. It proves our ancestors understood something we've forgotten, that the ultimate economy isn't reducing production costs. It's building something so well you never have to build it again. The looms are still there, still running, waiting to outlive us all.